Welcome back, friends. Dr. Boroli is here. Today we are discussing about the full wave rectifier with center tap. The circuit diagram is shown here. It consists of a transformer with center tap secondary. It is a step down transformer having two equal half of secondary windings VAO and VBO. When the input voltage 230 volt AC single phase is applied to the primary, the step down voltage, say 15 volt RMS, is induced across the secondary winding VAO and VBO. As we know that the center tap transformer provides 180-degree phase shifted voltage, that is VAO and VBO are 180-degree phase shifted. Diode D1 and D2 are the rectifier diode, and load RL represents the load on this rectifier. Vs is the secondary voltage, and we will treat it as input voltage to a center tap rectifier. Let us understand the operation of the circuit. We will divide the operation over the two cycles. First, positive half cycle from 0 to pi, and second, negative half cycle from pi to 2 pi. Let us see what happens during the positive half cycle, the interval 0 to pi of the input signal. It is shown here. During positive half cycle, the secondary voltage VAO is in phase with the input primary voltage, and VBO is 180-degree phase shifted with the primary voltage. VAO is positive going during positive half cycle, therefore diode D1 gets the forward bias, whereas D2 gets the reverse bias. Therefore, diode D1 goes in on state, whereas D2 goes in off state. When diode is going in on state, the current is flowing from upper half of the secondary from point A, then through diode D1, then through load resistance, back to the center tap and upper half of the secondary winding. This current is denoted as ILDC. Since diode acts as a closed switch, we will say that the voltage VAO is appearing across the load resistance. Practically, this diode D1 in forward bias have finite forward resistance, as well as the secondary winding also have some finite winding resistance, and therefore the current flowing through the load is decided by the peak value of VAO divided by RS plus RF plus RL, and that is the peak value of the load current. Whereas the wave shape of the load voltage across the load is same as the wave shape of the secondary voltage during positive half cycle. Thus, we can say that during positive half cycle of the input, we are getting positive half cycle of the output. During negative half cycle, we will see here a shaded portion of the wave from pi to 2 pi interval. The secondary voltage VAO goes negative, whereas VBO goes positive. Therefore, diode D2 goes in forward bias state and hence becomes on, whereas diode D1 goes in the reverse bias state and therefore it acts as an open switch, and therefore diode D2 conducts the current from lower half of the secondary to the point B, then through diode, then top end of the load resistance and back to the center tap and back to the lower half of the winding. Here you will see that during positive half cycle, the current is going from center tap to point A via secondary winding upper portion, And during negative half cycle, the current is going from the center tap to point B, that is 180-degree phase shifted in upper half and lower half. So during negative half cycle, we conclude that the voltage VBO is appearing across the load. Practically, this voltage is slightly less than VBO peak value because there is a forward voltage drop across the diode. So load voltage is less than the peak value of VBO by the amount equal to forward voltage drop of the diode. For all practical purposes, we ignore the forward voltage drop of the diode, and therefore we approximately say that VBO peak value is appearing across the load with top end of the load positive with respect to the bottom end, and therefore during both the half cycle we observe that the current flowing through the load as well as voltage developed across the load is in positive direction only. And therefore, we can say that the input AC cycle will be rectified in both the half cycles and available at the output as a DC wave. And therefore, this rectifier is called as full wave rectifier. The following figure shows the waveforms at various points. So see the figure on right hand side. Here during positive half cycle from 0 to pi of the input signal here shown in the first wave, we will see that diode D1 is on, therefore it connects point A to the load and therefore load voltage is same as the secondary voltage Vm sin of omega t that is shown here in the third waveform from 0 to pi. During negative half cycle of the signal, diode D2 is on and D1 is off, and therefore D2 connects VBO across the load. And therefore, here VBO waveform is shown from pi to 2 pi. We will see that VBO is going positive and the same part is appear here across the load from pi to 2 pi. And therefore, over one cycle of the input, we will get the two halves rectified at the output, and therefore this will be the full wave rectifier. The voltage waveform is known. The current waveform can be easily obtained with the resistive load by using Ohm's law. Here the waveform of the load current is shown in the last waveform graph. Im sin of omega t is the current flowing through the load during 0 to pi interval as well as from pi to 2 pi interval, where Im is given by Vm divided by secondary resistance plus forward resistance of the diode plus the load resistance. We will note here that only one diode is conducting during the respective half cycle and therefore diode current is flowing only in the respective half cycle, that is shown here as current through diode D1 and current through diode D2. Let us now study the performance parameter of full wave rectifier. Here, for the sake of simplicity, the waveform of the load current is reproduced. The peak value is Im and the nature of the wave shape is represented by Im sin of omega t from 0 to pi as well as from pi to 2 pi it is again Im sin of omega t, whereas Im is given by Vm divided by Rs plus Ra plus RL. It can be approximated as Vm by RL since Rs plus Rf is much less than RL, whichever may be the case. If RS plus RF is not ignorable compared to RL, then you have to consider it in the calculation. Now let us find out the average value of this load current denoted as ILDC. So ILDC is given by 1 by pi 0 to pi Im sine of omega t d omega t. Im is constant, so take it out of the integral sign. Sine omega t integral is minus cos of omega t with the limit 0 to pi. Therefore, after putting the limit, we get ILDC is equal to minus Im by pi cos of pi minus cos of 0, and that is equal to minus Im by pi into minus 2. So that is twice Im by pi. So we got the average load current value. Now let us find out the average load voltage VLDC. It can be very easy by using Ohm's law. We know V is equal to I into R. So VLDC is therefore equal to ILDC into RL. Substitute the value of ILDC, that is twice Im by pi. And therefore VLDC becomes twice Im by pi into RL, where Im is equal to Vm divided by Rs plus Rf plus RL. Whereas if Rs plus Rf is much less than RL, then VLDC comes out to be approximately twice Vm by pi. RMS value of the load current now. Let us find out IL RMS. Again, we will repeat here that IL RMS is the RMS value, that is root mean square. It is a square root of mean of square of the function. And therefore, your function is Im sine of omega t. So therefore, average value of this Im square sine square omega t is 1 by pi 0 to pi integral Im square sine square omega t d omega t under the radical sign. Im square is constant, so take it out of the integral. So therefore, under radical sign, Im square by pi interval 0 to pi sine square omega t will be replaced by 1 minus cos of 2 omega t by 2 and the integral d omega t. Now find the integral Im square by 2 pi here under radical sign in bracket omega t minus sine of 2 omega t by 2 interval 0 to pi. So it becomes under radical sign Im square by 2 pi in bracket pi minus sine of 2 pi by 2. Sine of n pi is 0 and therefore sine 2 pi by 2 term is 0. And therefore we got the real RMS value equal to Im by root 2. Similarly, we can find out the fourth parameter RMS load voltage value, that is VLRMS, and it is obtained by using Ohm's law. VLRMS is equal to ILRMS into RL, whereas ILRMS is Im by root 2 into RL. Substitute the value of Im, that is Vm upon Rs plus Rf plus RL, and therefore VLRMS is coming out to be Vm by root 2. The fifth performance parameter is a ripple factor and denoted by a small letter r, and it is defined as RMS value of the AC component at the output divided by the DC component present at the output, and it is defined as under root VL RMS square minus VLDC square divided by VLDC. Substitute the value of VL RMS and VLDC here and simplify. We will get ripple factor equal to 0.48 or 48%. It indicates that the full wave rectifier with center tap transformer provides 48% ripple in the output. In half wave rectifier, we have seen that this ripple factor is 121%. Compared to that, this rectifier performs better. It will reduce the ripple present at the output, which is an unwanted component. Next, we want to evaluate the rectification efficiency of the transformer. And the efficiency is defined as ratio of output power to input power. And therefore, we have to estimate the DC output power PLDC and the AC input power PAC. Let us find out the DC output power PLDC. That is simply PLDC equal to ILDC square into RL. Whereas ILDC we have already obtained, that is twice Im by pi square, and therefore PLDC is twice Im by pi square into RL. Similarly, the AC power PAC is the power supplied by the secondary to the total load on secondary, and the load on secondary is the practical resistance of the secondary winding Rs plus forward resistance of the diode and the load resistance, and therefore PAC is given by Is RMS square into Rs plus Ra plus RL. But Is RMS square or Is RMS is Im by root 2, and therefore Is RMS square is Im by root 2 square. Therefore, PAC is equal to Im by root 2 square into RL. Now, substitute these two values in the formula of power conversion efficiency, eta, that is defined as DC power output by AC power input. So, ratio of PLDC to PLAC by substituting PLDC and PLAC in this equation comes out to be 0.81 or 81%. This indicates that this rectifier converts the AC quantity or AC signal from the secondary winding to effective DC output power up to 81%. Only 19% power will be lost compared to half wave rectifier where the efficiency is around 41%. Here the efficiency goes up to 81%. So full wave conversion is having more efficiency or at least double efficiency compared to half wave rectifier, and hence it is better. Transformer utilization factor of a center tap full wave rectifier. It is defined as TUF is equal to DC power output by volt ampere rating of the secondary. So it is PLDC by PS RMS, where PLDC is the DC power available from the rectifier and PS RMS is the secondary VA rating of the transformer. So PLDC can be twice Vm by pi into twice Im by pi, or it can be obtained from equation number 6. Whereas PS RMS is the RMS value of the secondary voltage into RMS value of the secondary current into 2, because there are two half of the secondaries. And therefore it comes out to be 57.3%. So we can conclude that this center tap rectifier can utilize the transformer resource up to 57.3% only. The peak inverse voltage appearing across the off-state diode is observed to be twice of Vm, and the ripple frequency will be 100 Hz as observed from the waveforms. So friends, today we have seen the center tap, full wave rectifier, its operation and various performance parameter. And we come to the conclusion that the full wave center tap rectifier is better than half wave rectifier from the ripple factor point of view and conversion efficiency point of view. But the transformer utilization factor, even though it is better than half wave rectifier, but still it is lesser. And therefore, this configuration is also rarely used in practice because it demands for dual secondary winding transformer and which is having larger volume and bulky to place on electronic circuit. So that's all for in today. We will stop here. Bye bye.